Michael, can't really trust nobody with all this jewelry on you. My roof look like a no-show. Got diamonds by the bolo. Come with the Tony Homo for clowns and all the balls. Oh, I ain't pick on a psycho. Lil' mama bad like Michael. Can't really trust nobody with all this jewelry on you. My roof look like a no-show. Got diamonds by.
Here's your video on an introduction to exponential functions. This is one of the last main types of parent functions we're going to be doing. The only other one left is the logarithmic function. So in class, you already did the graphing exploration sheet where you graphed 5 functions on the front of the sheet. On the back, you graphed a few more. You had tables and you had matching. So you should have noticed some things whenever you were completing this worksheet in your groups. And remember, you did this without a calculator. The goal is to graph these without a calculator and to understand how these functions work. So I'm going to point out a few things that you should have noticed from this worksheet. These are things you're going to need to know, and it's very important that you understand these things well, because if you don't know how these things work, they're going to be very difficult to graph, and we're going to slowly work our way up to more and more complicated exponential functions to graph by hand. So first of all, exponential function is any function in this form right here, a times b to the x. One thing that's really important to remember is if you're going to call a function exponential, there's a huge reason why we call a function exponential. There's the word exponent in it. The variable has to be in the exponent. If the variable is not in the exponent, it's not exponential. So just keep that in mind here. Something you should have noticed is whenever you have a value out front here that's multiplied by the base, this number ends up being the y-intercept whenever you graph it. Whenever you do applications, which we will be doing very soon, a will represent the initial value of whatever you are studying or looking at. It could be an animal breed, it could be an amount of bacteria, anything. Whenever you graph, b is called, you might want to note that this is the base because it's the number that has the exponent. That's your growth or decay factor. You should have also noticed that if your base is larger than 1, you're going to see growth. If your base is between 0 and 1, you're going to be seeing decay. Growth would be as x increases, then your y values also increase. And decay would be as x increases, it's going to swoop down here, y decreases. Something to notice is that if you're talking about exponential growth is actually the most powerful growth out there. It grows quicker than a polynomial. It grows quicker than any kind of quadratic. Nothing grows faster than an exponential. So that is why they start off kind of leveling off and then they go quicker, 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 and they fly up like this. If you study something called a half-life in chemistry, that would be something like this where you're decreasing and then you eventually level off. And speaking of leveling off, all exponential functions have a horizontal asymptote, no matter what you do to it. You can stretch it, shrink it, reflect it. It's going to have a y-intercept. That's where the y values level off at. Let's see here. Let's look at a few of the graphs that you actually did on the sheet. So 2 to the x, 3 to the x, 4 to the x. So here they are. 2 to the x is red, 3 to the x is green, 4 to the x is blue. Notice they all have this horizontal asymptote of 0. They all have the same y-intercept, and the y-intercept is 1. And the reason why the y-intercept is 1 is because if you look at something like 2 to the x, this is not a, this is b. There's an invisible a here. It's actually a 1, which is times 2 to the x. So if you ever see something where it looks like there's not an a value, there is. It's just the a value is 1. So speaking of these here, where b is greater than 1, let's talk about growth first. The y-intercept is going to be 1 because there's no a value there. And one thing you should have realized here is that as your base gets larger and larger and larger, so b is going from 2 to 3 to 4, the graph is growing quicker and quicker and quicker. So let's take a look at 4 to the x. 4 to the x lays, or it gets closer to the x-axis for longer, and then it goes to the same y-intercept and shoots up way faster than 2 to the x. If I graphed like y equals 10 to the x, then that's going to be even closer to the origin here and then spike up. So let's make a note of that here. If you haven't already paused the video and gotten caught up to this point with me, pause the video now and do so. Make sure you're writing all the notes down. Don't skimp here. Okay, so for b to the x, for growth here, where b is greater than 1, as the base increases, the function is steeper. So visually, it's steeper. What's really happening is it grows faster, at a faster rate, however you want to word it. Now let's take a look at a half to the x, a third of the x, and a fourth to the x. So on the paper, you did a half and a third. Here I did a half, a third, and a fourth all to the x. This is the one that people mixed up a little bit more than growth. So here I have a decimal value of 0.5 to the x, and you can see that that is this decay right here. Again, they all have the same horizontal asymptote of y equals 0. They all have the same y-intercept of 0, 1. When I go from a half to a third, my graph is decreasing at a quicker rate, and it still levels off at 0, but it's steeper here. As I go to an even smaller decimal, 0.25 to the x, it's decreasing at an even faster rate. It still levels off, but if I were to do something like y equals 1/10 to the x, that's going to be a super steep decay here. This is decay again. So let's make a note of that so you remember that. So for y equals b to the x, where b is less than 1, the y-intercept is still 1. And as b decreases, meaning it gets closer to 0, the function is steeper. But when we say steeper this time, we mean it decays faster, not grows faster. So now I want to look at something here. You may have noticed this already. Let's look at a half to the x, 2 to the x, and 2 to the negative x. Here I have 1/2 to the x. Let's go ahead and graph 2 raised to the, that would be 2 to the x right there. I don't want 2 to the x. I want 2 to the negative x. Holy moly, it was the exact same thing as 1/2 to the x. How on earth is it possible that 1/2 to the x is the same exact thing as 2 to the negative x? We're going to look at that in a moment. I want you to also take a look at what would happen if instead of like 2 to the x, which is that, what if I did negative, whoop, oh my gosh, look at that. So there's 2 to the x, negative 2 to the x. Same horizontal asymptote, it's just a reflection. So if you put the negative up front, it's going to reflect over the x-axis. If you put the negative right by the x, it's going to reflect it over the y-axis. All right, now algebraically, there is a reason why a half to the x and 2 to the negative x are the same. And this is something that's really important that you realize. Let me move this up a tiny bit here. Okay, so make sure you write this down because, again, this is something I'm going to expect you to know. So let's take a look at 2 to the negative x. Well, by now, you better all know that to get rid of a negative exponent, you're going to put the exponential term with its base in the denominator, leaving only a 1 in the numerator. So that's 1 over 2 to the x. Now, 2 to the x is going to be something, I don't know what it is because I don't know what x is, but I want you to take a moment and think about, like, what would you get if you did 1 to the x power? It could be 1 squared, it could be 1 to the 10th, it could be 1 to the 1000th. It doesn't matter what x is, it's always going to be 1 because 1 to anything is 1. So 1 over 2 to the x is the same as 1/2 to the x because remember your exponent rules here. 1/2 to the x means 1 to the x over 2 to the x, and 1 to the x is just 1. So that is why 2 to the negative x is the same as 1/2 to the x. The same applies for pretty much any other number out there. It's not like it only works for a half. If you did something like a third to the x and then y equals 3 to the negative x, those would be the same thing. So even though you might be looking at your base saying like, oh, that base is bigger than 1, that's going to be growth. If you have a negative in front, so there would be like 3 to the x, the negative in front reflects over the y-axis, so now it looks like this, which is the same exact thing as 1/3 to the x. So those are all important things that you need to notice. Can you also make sure that you wrote this down? I really didn't comment on this, but we're going to talk about it in just a second, actually. B to the x, whenever you graph this, it's always going to go through 0, 1 because, well, that's your y-intercept. The y-intercept is 1. A is 1 out front. It's 1 times b to the x. And then you're going to have the point 1 comma b. If you have a times b to the x, a is going to be your y-intercept. So you go through 0a. And whenever you plug 1 in, so a times b to the first power, well, b to the first power is b, so you're going to get a times b. We're always going to plot these 2 points, the y-intercept and whenever x is 1, and we're going to do another point, which I'll tell you about in a moment. Let's move down here. Okay, so whenever we're reflecting the exponential b to the x, negative b to the x reflects the graph over the x-axis, and b to the negative x reflects over the y-axis. Alrighty, so this right here would be y equals negative b to the x, and then this right here, let's reflect over the y-axis. Well, it's not a very good exponential graph, is it? Woo. That is y equals b to the negative x. So make sure you sketch those and include that. One last thing is the tables. Well, actually, there's 2 more things here. For the tables, can you get out the worksheet that you did in class and flip to the back? I want you to check your answers now. You're often going to get a table of values, and you're going to need to write an equation for the exponential function that would model those points. Easiest thing to do first is to get the y-intercept. So remember, we're going to fill in here. The y-intercept is a. So just literally look at when x is 0, what's y. That's your y-intercept. Then you're going to have to decide, okay, is it growth or decay? Meaning, is b bigger than 1 or less than 1? And what do you multiply or divide by each time to go from y value to y value, or output to output? So in the first table, your y-intercept was 2. To go from y value to y value, you're multiplying by 2. So it's going to be 2 to the x. For the second one, your y-intercept is 4. To go from output to output, you multiply by 3. So it's 3 to the x. For the third one, the y-intercept is 3. To go from y value to y value, you could think, oh, I'm dividing by 4. But you really want to think, like, what am I multiplying by? And it's 1/4. Notice this is less than 1, obviously, because it's decay. For the fourth one, it's decay again. My y-intercept is 1. I'm dividing by 3, meaning I multiply by 1/3. And for my last table, my y-intercept is 5. To go from y value to y value, it's growth. I'm multiplying by 5. Notice that 5 times 5 to the x. This is really 5 to the first power. That's 5 to the x power. If you have the same base, what do you do with those exponents? Well, that's the same as adding them. That'd be 5 to the x plus 1. Same thing here. 2 times 2 to the x. I have the same base. When you have the same base, to combine, you add your exponents. So it's good to notice that, like, oh, 2 times 2 to the x is the same as 2 to the 1 plus x, or this is the same as 2 to the x plus 1. When we start graphing these by hand, these things are going to jump out at you a little bit more. All right, last thing that we're going to need to know in order to graph these by hand is you can shift an exponential function up and down, just like any other parent function. That is going to be if you have a plus c or a minus c at the end. So obviously adding is going to move it up c units. Subtracting moves it down c units. Whatever c is, that's going to be the horizontal asymptote. Also, you can move these things left and right. So if I have this, so add these. If your plus or minus is with the x, plus c will move it left c units, and minus c will move it right c units. This is the exact same as when I had x squared, and then I had, like, oh, x minus 1 squared. That moved it right 1, whereas x plus 2 squared moved it left 1. It's just we don't have parentheses here. You're like put it in the exponent with the variable. All right, next video, I'm going to do 3 examples graphing with you, and then you should be good for the next class.